In section 1D, we discuss analyzing arguments. So we'll make a distinction between inductive arguments and deductive arguments. Then we'll learn how to assess inductive arguments for being weak or strong and deductive arguments for being valid and or sound. Okay, those things apply only to those arguments. An inductive argument can only be weak or strong. A deductive argument can only be valid or sound. We cannot mix those two classifications of those inductive and deductive arguments up. Now, an inductive argument is one that makes a general conclusion from specific premises. Okay, so the idea is that we might go about collecting information and then drawing a generalization about all the observations we made about something. In other words, if I went around the university and met all students on campus and they all seem to share this same trait, maybe they all wear Vans skate shoes, then we would accept that Vans, we might generally conclude that all students wear Vans. So that's going specifically from student to student to make the observation, generalizing the conclusion that all students wear these shoes. Okay, so it's a delicate thing. You want to be careful with an inductive argument because it could be a hasty generalization, and you should have seen that by now in section 1A when we talked about fallacies. A hasty generalization is essentially a weak inductive argument. Now, a deductive argument is a more watertight situation, and mathematically, it's what's used throughout all of the theory of mathematics. So it makes a specific conclusion from more general premises. Okay, so we start from general and then go to small. So if we have a categorical proposition, all dogs are mammals. My pet is a dog, therefore my pet is a mammal. Okay, that is going from the general, all dogs, to speaking about my singular dog. So that makes it a deductive argument. Okay, I'll leave the example 1 to the student to discern, but you're asked to look at the cartoon above and determine whether or not that's an inductive or deductive argument being made by the stick figure. We'll move on to meet our first inductive argument, and really the only one that we're going to see. So again, an inductive argument can be evaluated only in terms of its strength. So it's either strong or weak. One of the best ways to break or to eliminate it or to just totally poke a hole in an inductive argument is to find a counterexample. So that's a really nice tactic. If there's a counterexample, a glaring counterexample especially, then it's quite clearly a weak argument because a counterexample exists. All right, but a lot of this is left up to judgment, and that's what makes inductive arguments somewhat difficult. So below, we're asked to evaluate the inductive argument we're given. So let's confirm that it is an inductive argument. We have 3 premises. Each one of these premises is a single mathematical difference equality, right? So 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 6 is 9. Okay, so we've gathered this information, and what we're suggesting somewhat in this argument is to say that, well, as we go further, we could do the next step. The reader could do that on their own. 36 minus 25 is 11. Okay, what do we see? We're getting odd numbers on the right. So it seems that the difference of any 2 perfect squares is an odd number. Okay, well, in the list that we have, we've got 4 examples. That's great, but the weak part of this argument is the fact that there are infinitely many perfect squares in the set of all numbers, and to go through and confirm that the difference of any 2 perfect squares is an odd number is a daunting task, and we only have 4 examples in front of us. We haven't even presented a drop in the bucket here. So the thing that we might look for is it might seem like a reasonably strong argument at the moment, but what we're going to look for is possibly a counterexample. Okay, how could we break this conclusion? We need to find 2 perfect squares whose difference is not an odd number. Okay, if we can find that, we have a counterexample, and then we've completely broken the inductive argument. We can call it a weak argument. Well, it turns out if we look at 16 and 4, so the only reason that all of these perfect squares had a difference that was an odd number was because they were consecutive perfect squares. 4 to 9, 9 to 16, 16 to 25 are all from one perfect square to the next. But it doesn't say any two consecutive perfect squares. It just says any two perfect squares. 16 and 4 are perfect squares, but we'll say this. We'll say note that 16 minus 4 equals 12. And this is exactly what we need, which is a difference of perfect squares and those being 16 and 4, that is even. Okay, so it's easy. Thus, this is a weak. The inductive argument is weak. That's what we'll say. Okay, so that just doesn't hold. Now, troublingly, if we were to continue on with every pair of difference of consecutive perfect squares on into infinity, we would get all of the odd numbers, 5, 7, 9, 11, 13. And that could be, you know, infinitely many examples that convince us that that conclusion is true. But the fact that we found a single one that doesn't hold, and it's actually pretty easy to find, we could say this is a weak argument. Okay. Now again, it was inductive because we went specifically, each of these cases we looked at, observations that we made, and we made a general conclusion about these things, difference of any two perfect squares. So our inductive argument, it was a weak one. We found a counterexample. Now, deductive arguments. So there are two criteria for evaluating a deductive argument, and they must go in order. So first, the argument needs to be determined whether or not the argument is valid. And that means that its conclusions or conclusion follows necessarily from its premises. Okay, in other words, logically valid is another way to say this, or logically true. Okay, so in other words, does it use good logic? Might be another way to say that for validity. After we've determined that the argument uses valid logic, the second thing to do, and it must come second, you can't assess soundness before validity, you have to check validity first, but if the argument is valid, then it will be sound if all of its premises are true. So there are two things here. The argument is sound if it is valid first and its premises are all true. If the argument is not valid, it cannot be sound. So we remember that. If it is not valid, it cannot be sound. It could be valid and not sound because it could check out to be valid, but it might turn out that the premises are not all true. Okay, so let's see an example below. So we're asked to analyze the deductive argument for validity and soundness. The easiest way to do this is with a Venn diagram. Okay, all animals with claws are potential human killers. Why are we motivated to assess this with a Venn diagram? Because we have a categorical proposition. All animals, right? We're starting off with the word all are something. So now we can use that categorical proposition to set up a Venn diagram. So it looks like animals with claws are human killers. So one set within the other in our all situation. Okay, and let's see. All animals with claws, so that's the inner set, because it's the first one. Claw animals, we'll call that. And then are human killers, that's the outer line, human killers. Okay, now let's see. We have my cat has claws. Okay, so this is a new one. We haven't dealt with an individual in a Venn diagram in too many cases so far, if any. So let's say this. We'll let X be my cat. Okay, now we need to place an X where my cat belongs in this Venn diagram. My cat has claws. That firmly puts my cat in the claw animal set. There's no question about whether or not it's outside of that set. It's the inner set, so it's there. Now the last thing we look at is the conclusion. my cat is a human killer. So we've concluded that my cat is a human killer. If we look at this set diagram down here, we realize that that must be the case. There's no way to be in the set of claw animals without being in the set of human killers. Okay, so the logic is valid, or the argument is valid. Is valid. Since the conclusion follows from the premises. Okay, so that's part one. Second, they ask us for soundness. Well, soundness, all we need to go through and do is check. So check the premises are true. Well, my cat has claws. That's believable enough. Okay, now all animals with claws are potential human killers. It could be argued that we'll even get rid of this troubling word right here. Maybe that just shouldn't be there. Are human killers? No, not necessarily. Okay, so the first premise seems untrue. Yeah, it doesn't hurt. Maybe we suggest something. You know, think hamster. Hamsters have claws. How many people have hamsters killed? Okay, so we conclude that the argument is not sound. It's not sound because one of the premises is untrue. So validity is always a firm conclusion one way or another. We can always check validity of an argument and know for sure whether it is or whether it is not. Soundness is a little bit more judgment on the reader's part, on the student's part. For the most part, I'll be quite forgiving with judgments of soundness, whether or not you accept a premise to be true or not. But validity should be it is always concrete, okay, to recognize valid logic. Okay, our next Venn diagram, our deductive argument with a Venn diagram. Here's the steps that we used in the previous problem. Let's just run through another one here. We're asked to determine the validity of the following argument and possibly to check the soundness of it. So for our given argument, where the first line we have is a vegan is a vegetarian. In other words, a vegan eats at most a vegetarian diet. So a vegan is a more restrictive version of a vegetarian. A vegan eats no animal products, whereas a vegetarian eats non-meat animal products. Okay, so a vegan, the set of all vegans, has a diet within the set of all vegetarians. Okay, the second, so that's the first premise here. And notice it's a categorical statement, and it could say all vegans are vegetarians, right? But it says a vegan is a vegetarian, so any single representative of one group is in the other one. All vegans are vegetarians. It's a nice way to infer that. So Ron Swanson is not a vegetarian. So we decisively put an X out here for Ron Swanson. Okay, X is equal to that. He's not a vegetarian, so we know that that X does not belong inside that outer circle. If it's not inside the outer circle, it can't, it's anywhere but inside the outer circle. It couldn't even be in the inner circle. Now the conclusion of this is that Ron Swanson is not a vegan, okay? But when we look at the picture, that's exactly what this is telling us. There's no way that X can be inside this set and still be outside of this set. So the logic is valid. The sets confirm that. So the logic is valid. The argument is valid. When we see a picture like this, we know that, yeah, we can accept that conclusion as logically valid. Now, soundness. Is it sound? So a vegan is a vegetarian. That's true in the sense that vegans have more restrictive diets. So that premise is fine. Ron Swanson is a famous fictitious character who's very much not a vegetarian. So both premises are acceptable. Both premises seem true. Once both premises are true and the argument is valid, we can conclude that the argument is sound. All right. So we have a sound argument now. Okay, and another way to check these, this is a nice trick to have around, is 4 basic conditional arguments: affirming the hypothesis, affirming the conclusion, denying the hypothesis, and denying the conclusion. Now, 2 of these work every time, are true, or valid logic. Affirming the hypothesis is valid, denying the conclusion is valid. Now, on the other hand, affirming the conclusion is invalid and denying the hypothesis is invalid as well. Okay, what does any of that mean? So many statements have an if P then Q situation. All P are Q satisfies this as well. If it's in P, then it's in Q, right? In terms of set theory, okay, or categorical propositions. Now, if P is true, then it must follow that Q is true, right? If it's a P, then it must be a Q. Okay, that's valid logic. On the other hand, just because it's a Q doesn't mean it's a P. So that's invalid logic if we try to go that direction. Denying the hypothesis, saying that it's not a P, so it must not be a Q. That's like saying, so if we start with if it's a P, then it's a Q, then we say it's not a P, so it can't be a Q, it's not necessarily true. And you might see that below. Denying the conclusion, on the other hand, if something is not a Q, then it can't be a P if it's given that if it's P, then it's Q. Okay, so because if it's this, it must be this one. So if it's not this one, there's no way it could have been this one, because if it's this one, it has to be this one. All right, so maybe with some flesh on the example, that might make a little more sense. The textbook could provide that probably in all 4 cases. Let's see. Consider the argument given below. Rephrase the premise so it has the structure if P, then Q. So we've done that here. We were given if you live in Boston, you live in Massachusetts. All we needed to do to rephrase that was add the word then. So we've got it. If Boston, then Massachusetts. And now identify the type of argument, determine its validity with a Venn diagram. So it's a deductive argument because, well, reading it through, if you live in Boston, for all people who live in Boston, they live in Massachusetts. Amanda does not live in Boston. Therefore, Amanda does not live in Massachusetts. We start with anybody who lives in Boston and end with this Amanda. So we're going from general to specific. So it's a deductive argument. Now to get back to set theory, all people in Boston live in Massachusetts. So if you live in Boston, then you live in Massachusetts. So there's Massachusetts. Within that is Boston. Geographically, that makes a lot of sense. Massachusetts, the outer side. Okay, so that's this premise taken care of. The second premise, Amanda does not live in Boston. The question is where to put Amanda's X. Okay, so it's not clear where to put Amanda's X. We know that she does not live in Boston. Let's make an X for her off to the side. This is Amanda. She doesn't live in Boston. So we know not to put it in here, but we're not sure because not living in Boston doesn't tell us anything about whether or not she lives in Massachusetts. So we should put that X right here in the border of Massachusetts and say she could be in Massachusetts, she might not be in Massachusetts. We don't know just because she's not in Boston. There are plenty of cities and towns in Boston that aren't, or Massachusetts that aren't Boston. So our conclusion, Amanda does not live in Massachusetts. Well, we don't know that. We couldn't conclude that when we made this drawing. So that's invalid logic. This is invalid. We'll call it an invalid argument. Okay, once we know that this thing is invalid, then we know that it can't be sound. The premises are acceptable. However, it's invalid, so it can't be sound. Remember that. So It's unsound. The argument is invalid. It must be unsound. Okay, and that fills out the rest of that. Now to think about this in terms of our structures above, we have if Boston, then Massachusetts. Okay, that's our if P, then Q. If Boston, then Massachusetts. What we have is that Amanda does not live in Boston. So this is not P. This is denying the hypothesis. Not P is not true. Not P. This is an invalid logical structure. It doesn't work. And we see why in the example below, why that wouldn't work. Just because you don't live in Boston doesn't mean you don't live in Massachusetts. So that's it. There's one more example. I'll leave that for students to do to determine whether or not the argument is valid, and then follow up with whether or not it's sound based on that. And there are plenty of other examples and exercises in the book and in the homework, so good luck with that.